let me see if that's what happened, and then I'll accept both answers
Okay.
because you know what, I had trouble seeing
So it is recording here. All right, so let's take a look at the comparison of acids and bases. A little comparison here. We know acids, after doing our calculations, are going to have a high concentration of hydrogen ions. Remember, in the brackets like that, we're talking about the molarity. Bases are going to have a high concentration of OH, hydroxide ions, or low hydrogen ions. Acids, high concentration of hydrogen ions, but low pH. Bases, high concentration of hydroxide ions, but high pH. Okay, when an acid is added to a solution, it's going to add those hydrogen ions. When a base is added, it will add hydroxide ions, but those hydroxide ions will usually combine with the hydrogen ions to make water and neutralize. Right. So an example of a strong acid we have here, hydrochloric acid. Example of a strong base we have is sodium hydroxide. But we don't care so much about the strong acids and bases if we're going to talk about buffers. We care about, like, what I like to say, weak acids and weak bases, but they don't call them weak bases, they call them conjugate bases. Weak acids and conjugate bases. Okay, they act as our buffers, especially in living things. Okay, so what are buffers? Buffers are substances like these weak acids and conjugate bases that will resist pH changes. They minimize the hydrogen ion changes. They accept hydrogen ions when acids are added, or they donate hydrogen ions when bases are added. And living things depend on these buffers to prevent these drastic changes. And we're constantly getting these drastic changes from both external and internal causes. For example, metabolism adds acids. Whether it be from lactic acid and exercise or digestive enzymes, sickness, stress, etc. So we'll go into like more examples of that in a moment. So let's take a look at the pH scale and blood. Okay, so blood has a pH of 7.4. It's actually not perfectly neutral like water, being 7.0. It's a 7.4. What does that mean? That our blood is slightly alkaline? It is, but that's how our blood needs to be, and we'll see why that is in a moment. How far alkaline can we go? We can only go up to about 7.8. Beyond that, you're going to die. But in between that 7.4 range and 7.8 range, that's called alkalosis. You have high blood pH, lower hydrogen ion concentration. That's not as common as acidosis, which is between the 7.4 and the 6.8 range. Beyond 6.8, again, you're going to die. But in that acidosis range, when you have low blood pH, you have higher ion concentration. Now, if you look to the side, I'm going to try and cover up one side so you're only concentrating on one side. We're going to cover up the alkalosis side. We're going to concentrate on what causes acidosis in the blood. And look at this list. It's long. Eating. How does eating cause it? Digestive enzymes are produced, as well as hydrochloric acid in the stomach. When those acids go up, they are going to diffuse into the blood and lower the pH. Exercise. Even if you are in the most wonderful aerobic condition that you can be in, you're still going to do a little bit of anaerobic respiration, which is going to produce that lactic acid. Drinking alcohol is a lot of acetic acid in alcohols. That is also going to lower the pH. Starving, here we're saying eating, but also starving. Starving, your body is still going to produce digestive enzymes, kind of like, are you sure something's not in there? They're going to produce those digestive enzymes. They're only going to diffuse into the blood. Hypoventilation, not to be confused with hyperventilation. That's like shallow breathing when like you're crying or even an asthma attack. And when you're shallow breathing, you're getting less oxygen into your body. And less oxygen is going to put you more into that anaerobic situation. So asthma, same thing. Cardiac failure. Again, you're going to have a buildup of carbon dioxide, less oxygen, more carbon dioxide because the heart is lowering in its capacity. Crying, we said that's shallow breathing, less oxygen, more carbon dioxide. Even normal metabolism adds acids and carbon dioxide as a result. Renal failure. When urine is not being properly removed, urine's very acidic, or when urine is not being removed and it's staying in the body, it's very acidic. It's adding to the acidosis and severe burn. So we have a long list of just normal things that go on in the body, but also like some trauma that happens to the body that can cause us to go into this acidosis phase. And again, our bodies have buffers to counteract this, but can only counteract it to a certain point when, hospitalization or medicines are needed otherwise than that. So let's look at the opposite side. The opposite side is the alkalosis side. What causes alkalosis? What causes your blood pH to raise, in other words, or rise? So alkalosis, it's a lot of the opposites. Low metabolism is going to cause alkalosis. Antacids, you're preventing acids. Depressants are going to slow down the metabolism. Vomiting is kind of an interesting one. At first, you would get rid of a lot of acids, and so you would be more alkaline, but eventually, with the absence of those acids, more would be produced. So vomiting initially starts out alkaline, making your body more alkaline, but then sends you into an acid kind of phase. Hyperventilation. This is that deep breathing where you're expelling a lot of carbon dioxide, and some people cry, like hyperventilate, kind of like, and if you're blowing out a lot of carbon dioxide. I think about when I used to swim. This is probably pretty bad, but when we did sprints, a lot of times we would hyperventilate before a sprint if it was only 2 laps because we didn't want to breathe during this sprint, which is really bad. They realized that, no, you do want to breathe, but we didn't want to breathe thinking it would slow down your momentum. So we'd hyperventilate to blow out the carbon dioxide so we'd be able to do 2 laps without taking a breath. And really bad. They realized that, no, that's not bad. You just got to get your momentum, but your breathing's got to be in that momentum now. IV injections, when you do go to the hospital, since most causes are going to be acid, adding acids to the body, IV injections definitely add more basic fluids to your body. And diuretics is going to remove the urine, remove the acids, and definitely send you more in the alkaline stage. So what are some human blood buffers? And I listed like a few of them right down here. Okay, so let's take a look at these. The most common ones, the most numerous ones, we should say, are these plasma proteins. We're not going to get into that, though, too much because they're a very diverse category of buffers there. And depending on if you're studying a specific metabolic pathway, then that pathway you would study the certain proteins that are in there. But we're not going to target any one in particular. But they are the most numerous. They are the ones that the body depends on more, but they're very diverse. Hemoglobin. I've heard of hemoglobin with red blood cells. Well, that's the iron ion that's in there. And that iron ion can work as a buffer as well in the blood. H3PO4, from chemistry, you might remember that's phosphoric acid. That will combine with any of your ammonia products to make your urine. That's a very slow process, actually. Now, I know you probably think you've got to go to the bathroom quite frequently, but it is very slow to process the metabolic waste. And metabolic waste in your blood usually have ammonia components to it, and that ammonia combines with the phosphoric acid to make the urine. But the one we're going to focus on is the carbonic acid system. I like to call it the soda water. It's soda water. It's like carbonated soda. And this is connected to the respiratory system and works very quickly. Okay. And just to point out that the phosphoric acid and the carbonic acid are your weak acid buffers. Up here, the plasma proteins and hemoglobin, those are both protein buffers. I know hemoglobin, the iron ion, is not the protein part of it, but the whole iron with the protein in there is the hemoglobin. Remember, proteins usually end in that IN sound. Okay, so we're going to focus on carbonic acid. All right, so that's my next page I'm going to take a look at here. And it's quite the balancing act when we look at carbonic acid. And we call it the carbonic acid / bicarbonate buffer system. So where am I getting bicarbonate from? So let's take a look at this equation here. Here's your carbonic acid. Okay, it's a weak acid. And when it's in aqueous form plus water, generally speaking, okay, it's going to shift to where we get this bicarbonate ion and this hydronium ion, which is just a hydroxide connected to a water molecule. And I kind of break it down here. We see a water, 2 hydrogens, and a carbonate ion. 1 hydrogen will attach to the water, 1 hydrogen will attach to the carbonate to make your bicarbonate plus your water and all. We usually cancel out the waters, and we'll see that a little bit later. Let me cover up some of this and not ruin the surprise that's coming up here. Okay, so as we look at this, how is this equation here going to keep us in balance, keep our pH in balance? Okay, so how are we going to keep that pH in balance with this? Well, I always think of this bicarbonate ion, and it's in a little greater concentration. Like if I was to say, is this perfectly balanced? No. There's a little bit more on this side, and that's why I drew this arrow more going this way. So that means there's a higher incidence or a higher concentration of the bicarbonate ion in our blood. And I call the bicarbonate ion the catcher in the blood. If you've ever read Catcher in the Rye, good old Holden Caulfield, he's got to catch those phonies falling off the cliff or the kids falling off the cliff. Anyway, that's another topic for an English class. The bicarbonate ion is going to be the catcher of the acids. You know how we said that so often acids are being produced from normal metabolism, eating, exercising, all these things, and trauma? The bicarbonate ion is your superhero. He's going to capture these acids and really do a conversion thing for you. So let's watch how that happens. So here's where we're pretending like you're exercising. So there you are, adding lactic acid, dropping acid. You're putting acid into your bodies like a drug addict or something. No, you're not. You're just simply exercising, and lactic acid is going into you. So we see this shift from bicarbonate being in a greater concentration, but it shifts. The bicarbonate starts, catching these hydrogen ions, and it shifts to more carbonic acid. So now when we have this increase in carbonic acid, well, it's like soda water. If you open up a soda, what happens? Well, it fizzes, right? So when you get too much carbonic acid in your blood, you actually start fizzing. That carbonic acid, will decompose, check this out, to water and carbon dioxide. And you will literally bubble carbon dioxide out of your blood. Blow that out, and the whole shift goes back again. So if you actually wonder why you breathe out carbon dioxide, yes, a little bit from respiration. We learn about oxygen, and we learn about aerobic respiration, anaerobic respiration, but you actually breathe more carbon dioxide out from all your metabolic processes that are dropping acid into your bloodstream, bicarbonate shift into the carbonic acid fizzing out that carbon dioxide, and you blowing out that carbon dioxide. So you really blow more carbon dioxide out of your body as a result of neutralizing acids that are always going on. So if we look at the whole balanced equation and we take out the unimportant parts of it, we look at this side over here, this side here, with the hydrogen ions and the bicarbonate, and that's what's generally pretty great in your body. That's like the highest concentration here. But the shift can happen to the carbonic acid, which shifts to the water and the carbon dioxide, and then it can shift back to like equalize it again. So this is our whole players when it comes to like neutralizing or buffering all those acids that you're doing from normal metabolism, from trauma, and all kinds of other things. So the song means we're almost over, and that's it, folks.